is about rational numbers as exponents. Right? Rational numbers as exponents. And I think that this title in itself, is a pretty interesting title because we take a look at rational, right? Right. We take a look at this rational here. Well, rational, if you recall from the previous chapter, is just a fancy way of saying fractions. Right. So all we're doing is we're looking at fractions as exponents. Right. We are looking at fractions that are in exponential form. Right. So once again, these are just exponents. Let me rephrase that. Exponential forms where the exponent is a fraction. An example is something maybe like 5, or let me go back and see, maybe something like 4 to the power of 1 over 2. Right? The entire thing is in exponential form. Right? We call the 4 the base. The 1/2 is our exponent. And as you can see, that exponent is a fraction. So this is kind of the material, the things that we're going to be looking at in this 6.2 section. Just looking at some exponential forms where exponent is a fraction. And believe it or not, this is something that we can actually simplify. One of the things is, first of all, you can put this in your calculator, right? A problem like this can be put in your calculator and you get an answer, right? But we can also do this without the use of a calculator. And that's what we're going to start with today. We're going to start with talking about, how we can go from exponential form to radical form. Right, we can go from exponential form to radical form. And not only that, but we can go the other way around as well. We can go from radical form, if we wanted to, exponential form. The general form of looking at this could be, exponential form. Maybe our base is a, and our fraction could be m over n. In regards of a radical form, but we need to have a radical symbol, right? Where our bases are radicand. Remember, we call that our radicand, would be a. The index or root is n, and that m is just the exponent of that radicand. A very important property. You are going to want to make sure you know this property extremely well. Because that's how your homework starts, right? Your homework will ask you to go from one form to the other. Example. Write as a radical. X to the power of 1 over 5. So it looks like this, right? It looks like this. We want to turn it to like that, right? Currently looks like a exponential form. We want to write it as a radical. So doing that means we need to have a radical symbol. Our index is 5. Our radicand is x. And we give x that power of 1. We can really just simplify this and say the 5th root. X to the power 1 is just x. Any questions with that example? Also, I want you to note that 5 is an index. Okay? This, notice how that 5 is in front of that radical symbol. That would be wrong. That 5 has to go inside that radical symbol. You'll notice on my Labs Plus and even on your calculator, usually have something maybe that looks like this, where you got to put a number in there and a number in there. All right. So be very careful, okay? Any questions with that first example? All right. We should be able to go the other way, right? Next example, I want you to write with rational exponents. Right, so we want to write with rational exponents. I give you something maybe like square root of 11. Right, so now I want you to show this to me in exponential form. Right, I want you to show this to me in exponential form. So if we take a look back at that property, right, taking a look back at that property, now what we're doing here is we have something that looks like this, and we want to make it look like that. Right? But you may be saying, where in the world is this M? I don't see that in that problem. Where in the world is this N? I don't see that in that problem. Right? That problem is only really giving us the A. And this is why I like that problem, because you need to understand a couple of things. Well, if you take a look at the previous example, notice that that 1 is really there, right? If it doesn't show anything, it means it's a 1. So when we go back to our problem, that implies that it has a power of 1. But now the question is, what is our index? Right? I think I talked about this, when I discussed 6.1. If no index is present, that means that the index here is a what, y'all?
A 2.
Is a 2. Very good. Right? So that means that we have a 1 here and we have a 2 there. Now we have all the information that we need. And now from there, we can go ahead and show this as a rational exponent, 11 to the power of 1 over 2. Any questions with this example? So we start off with this property. Knowing this property is going to be really important as we continue on. Questions with these first 2 examples. That's maybe what your first 4 problems will look like. Okay, then after that, we will review a little bit of the laws of cosine, laws of exponents. And I just want to mention, that this is review. These laws of exponents is something that's taught. This is taught in a Algebra 2 class. So I would strongly encourage you, because I'm going to do these problems pretty quickly. Everyone who's in this class means they're either TSI satisfied, they pass college, or they pass the TSI. They know Algebra 2. They know this stuff, right? If you're in this class, from maybe passing 0314, well, then that means you learned it in 0314, right? So I would encourage you to spend some time reviewing these, but we have a few of them. The first one is the product rule. Right, we discussed this one already. A to the power of m times a to the power of n means we just add them. Second one looks like it's the quotient rule. We've taken a look at this one as well. A to the power of m over a to the power of n means we just subtract these exponents. Now it looks like we have the power rule. Open parentheses, a to the power of m, close parentheses to the power of n means that we multiply those exponents. Another version of the power rule, right? Say power rule here, power rule there, is maybe if we had it in like a fraction or two terms in there, a, b to the power of m means that we give each one of them that m exponent. Another version of it is maybe if it looks like a fraction. Once again, we give each one of those terms, one on the top and one on the bottom, that exponent. And I think the last one is the negative exponent rule. Something like a to the power of negative n, right, is the same thing like 1 over a to the power of n. And that can be extended, right, in a few ways. Maybe a over b to the power of negative n. Right, let me just flip the inside, make that positive. So some important rules. Once again, I encourage you to review those rules. You can always send me an email, and I can have a whole bunch more examples of looking at these rules. Really important rules here, and we're going to look at a few examples applying these rules. All right, so let's take a look at some examples here. Does anyone need another minute copying these rules down?
Yes.
All right, just let me know when you're done, please.
Okay.
All right. All right, so let's take a look at some examples here. We are going to, this example asks to rewrite with positive exponents. I give you 7x to the power of negative 1 over 9. All right, so I want you to rewrite this with positive exponents, which means I don't want this exponent of -1/9. I want to make it positive. Right? And remember that our negative exponent rule, one of them tells us, hey, if we have a negative exponent, we can definitely make it positive by relocating. All right. So we take a look at our problem. We have 7x to the power of -1/9. I'm going to kind of put this over 1. Okay. And now I notice that my x has a negative exponent. So now all I'm going to do there is relocate that to the bottom. Right? Therefore, 7 stays on the top. We have x to the power. When we relocate it to the bottom, it turns positive. So a nice little example of how we can rewrite a problem with positive exponents. Any questions with this example here? Any questions?
I have one question.
Yes, sir.
So if it's always negative on the top, it becomes positive on the bottom. Can you transfer?
Correct. Correct. Because once again, the problem says write it with positive exponents, which means you have to relocate it. If it was on the top, you put it on the bottom and make it positive. If it was in the bottom, you would put it in the where?
Put it on the top.
There you go. Change it to positive. Very good. Good, good, good. Other questions? All right, next example. Simplify. 8 to the power of 14/3 times 8 to the power of 5/6. So in this example here, what we're doing is we are multiplying these two exponential forms. And we saw this this property that says, hey, when the bases are the same, all you have to do is add those exponents. Right? So this is just going to be a to the power of 14/3 plus 5/6, where we're adding unlike fractions. Right? So you should be able to add these numbers. I mean, obviously your calculator will do it for you, but if you are a STEM major and you're taking pre-calculus, you need to know how to do this. Right? There's no way, y'all, you take pre-calculus, you're not using a calculator at all. Mr. Corey's not letting you. He's the only one who teaches it. Right? So you need to be able to do this without using a calculator. Right? Which means finding the LCD, multiply the top and bottom by 2. Right? Giving you 28 plus 5/6. And what do you get? 28, 29, 30, 31, 32, 33. Right? And I think even that reduces, doesn't it? Right? We can divide each one by what? By 3. Giving us 8 to the power of 11. Any questions, y'all, with that example? All right. So a few examples there. What about this example here? Here I ask you to use rational exponents to simplify. I want you to use rational exponents to simplify. Right? So make sure you really understand the directions. The directions say, hey, let's write these in exponential form. Right? Let's write this in exponential form. So we want to write it in exponential form. That means that we're going from the property that we discussed earlier, right? We're using this property. The issue here is we don't see an index. We don't see an index. That means the index is what? What's that number?
2.
Very good. Right? So now what we want to do is we want to go from, once again, we want to go from it looking like this to looking like that. All right? So if we do that, right, looks like it's going to be x to the power of 12 over 2, y to the power of 4 over 2. And now from there, you can just reduce these. Reducing them gives us x to the power of 6 and y to the power of 2. Any questions there, y'all? Any questions? Right. So 6.2 is a really nice section. We start looking at radicals, rationals a little bit more. And I really like to end 6.2 with this example. Because what if it doesn't divide nicely? Right? What if you cannot divide that? Right? So my question here, right, and this is what I want you to start thinking about, is what if you had this? $13 divided by 2, 5 divided by 2 is not very nice. Doesn't give you a whole number. So what does that mean? Does that mean you cannot do anything? And that answer is no. You can still simplify. And that is what 6.3 is all about. And that's what we will start discussing. But before I do, any questions so far?